Yeah, I can move it there for now. Welcome, Exam 1, 6002 review session. How this is going to work, we'll quickly review what topics we're doing. Can everyone hear? Is this good? Okay. We're going to review what topics there are, then we'll kind of spend a couple minutes going through each topic, and we'll intersperse that with some problems.
And please, at any time, if you have a question, just ask.
Yeah. The worst thing you can do is like sit there and be confused about what we're doing, because maybe what we're doing doesn't make sense. So make sure like you're checking yourself at each point to make sure you understand what's happening. Yeah, and then we'll have some time at the end for questions, sort of thing. But yeah, interact with questions throughout the whole thing. Okay.
Yeah, so this is the list of topics that we've covered thus far. So we have KCL and KVL, series and parallel combinations, nodal analysis that involves supernodes, matrix method that relates to nodal analysis. We've covered superposition, and that then ties into Thevenin and Norton equivalence. We've talked about dependent sources. Those show up in a lot of different places, op-amps, and then most recently RC circuits. So just basic beginning of the semester stuff. So one thing that's super important whenever you're solving any circuit is to be very, very precise and consistent in terms of your directions of current and positives and negatives for voltage. So generally, the rule of thumb we use is that if you have a component, right, we have our voltage across it, that you can define in any direction. We always say that the device current flows into the positive terminal and out the bottom terminal. So that is always how we define these things. That will become very relevant, especially if you're talking about things like power, right? If you want to know how much power is being dissipated by something, right, if the power is positive, then it's being dissipated, whereas if the power is negative in your calculation, then it's being supplied. That positive and negative is only going to work out that way if you always have the current going into the positive terminal of the device. So just make sure to be super consistent with that. That then shows up whenever you're solving a circuit, especially with nodal analysis. So KCL and KVL should be pretty intuitive at this point, but if we have any node, right, and we have these three currents, then we always have, I1 plus I2 plus I3 equals 0. And of course, that's only going to work because all three of those currents are pointing in the same direction, right? So if we were to reverse the direction of I1, say, physically nothing changed in the circuit, right? We've just labeled this circuit, we've labeled it with these three different currents, and we've just defined them to be going in certain directions. Physically nothing's changing, but in terms of our equation, we now need a minus sign in front of I1. Yeah. For KVL, that is around any loop. If we have some set of components, it can be any number of components. What's key is that they form some closed loop, right? Then if we have, V1 across one component and V2 across another component and V3 across another, then the total voltage around that loop is going to add up to 0, right? Because voltage is always a differential reading, so if you get back to the place you started, you've got to be at 0. One key, same thing in terms of all of this directionality and making sure you're consistent with your signs. Whenever you want to do KVL around a loop, choose a direction. It can either be clockwise or counterclockwise, it doesn't matter. And then the go-to rule of thumb is if you've reached the positive terminal of a device before the negative terminal, add it. If you reach the negative terminal first, subtract it. So, if we go clockwise around this loop, for component V2, right, we're going to reach the positive terminal first, so we'll have a plus V2. For V3 here, we hit the negative terminal first, so we'll do minus V3. And for V1, we hit the negative terminal first, so we'll do minus V1, and that's going to equal 0. So super, super important to just set everything up, to define your variables, keep them in the same directions, and just be consistent with how you do these pluses and minuses. And that should help you with all of these different problems.
So continuing from here.
I have a question.
Yeah.
So with something like a resistor, which either no matter which side like the current goes into, it's going to be a voltage drop. Do you still define it like with the plus and minus depending on whether you go to the positive or negative terminal?
Yeah, so it's a good question because it brings up, right, like when we've been given a circuit, sometimes we've just sort of defined some current going in some direction, right? And so there's always sort of this notion of every component has its own voltage drop and current through it. And so, right, if we have a resistor, then if we've defined some, current going this way, and the plus and minus V, and this is resistor R, then we will have that, that V equals I1 times R. If this I1 were pointing in the other direction, then we would have a negative sign here.
Even though there's no way for a resistor to be supplying voltage.
Right, and the idea behind that is that, right, like V and I1 could be negative. Like just because we've called something the positive direction, that doesn't really mean anything. If I give you a physical circuit and then I draw it on a piece of paper and I, label some current going one direction, I could just as easily label it going the other direction, then it would just be the negative value of the first one. Yeah?
How do you determine which side you're going to consider as the positive and negative?
It's also a good question. That's pretty arbitrary. You can kind of do whichever one you want. Sometimes if you're given a problem, like an independent voltage source, right, that has the positive and the negative already defined because it's telling you which side has the greater voltage by whatever amount is listed. But if you're just like given a resistor and there's no polarity already given to you, you can define either side as the plus or the minus. And right, it makes sense because the if we were to define the voltage in the opposite direction, then we would get another minus sign, right? Because we just flipped that, but if you notice, I could have just as easily drawn the I1 over here, and then we would have our normal situation where the current was going into the positive side, and we could drop both negatives. But the idea is that you can sort of define these currents and voltages in your circuit whichever directions you want, but once you've defined them, you have to keep them however you've defined them, and then the positive and the negatives should follow from whether the current's going into the positive or negative terminal of your devices. We good? All right.
So the second part of this is power, and we'll just review that really briefly. So when we're talking about power with this kind of device, again, plus, minus, and I is going into the device, and we have V across. So we've written power is equal to I times V. We can also use this relationship and find that it's equal to V squared over R if we're looking at a resistor, or it's equal to I squared. I squared R.
One important thing to note about that, oftentimes, you see V squared R or I squared R, and that's often easier to solve for in a circuit than I times V, just because, right, presumably you've been given the resistance R, and so solving for V squared over R, I squared R only requires solving for V or I, whereas I times V, you've got to solve for both. It's important to note, though, that these aren't some like fancy equations that we've derived. This is literally just, if we replace the V with IR, since it's a resistor, we get I squared R. And if we replace the I with V over R, because it's a resistor, we get V squared over R. And those simplifications only work because this is a resistor. So if it were any other component that doesn't have a resistance R, the general definition is I times V.
And then, so furthermore, when we're talking about power delivery, and this goes back to why you need to be really, really careful about what signs you're using. If we've defined I to be into the device and V to be across the device in this manner, then we can think about whether power is delivered to the device or supplied by the device by looking at the product of I times V. So if we're using these ones, since you have like V squared and R is always positive and I squared and R is always positive, these are never going to tell you the sign of your power delivery. So when you're doing that, you really need to think about this I times V to make sure you have the sign right. So if I is going into the device and V is across in this manner, power is being delivered to the device. So this device is using power. So this would occur if I is positive and V is positive. So that would be these two quadrants would be power is positive, meaning it's delivered to the device.
Right.
And
The way to think about it is I times V, right? We always say it equals power, but does that mean power supplied or power consumed? I times V is the amount of power consumed by a device. So if you get a positive value, it is consuming power. If you get a negative value, well, what does it mean to consume a negative amount of power? It's the same thing as supplying power. And as Hannah noted, with these special versions of the I times V formula for a resistor, R is going to be a positive value, and so will V squared or I squared, and so we're always going to get a positive value, and that makes sense because a resistor is always going to burn power. It's going to consume power. It's never going to be supplying power. So those are good sanity checks to do. So like if you're doing a problem and you notice that for a resistor you have V and I, one of them is positive and one of them is negative, you know that you've sort of flipped something somewhere. So yeah, little checks like that can be very helpful in larger circuits.
yeah. And furthermore, when you're doing the problem solving, they'll say the power supplied to device X or the power supplied by device X. And when you're doing that, I and V and R all refer to that device in particular. So that's a little bit on power, and then going back to Jacob's diagram here, just to get some terminology set. Can everyone see this? Is it large enough? You guys in the back? Yes? Thumbs up? Okay. So just to get terminology right, these, we talk about nodes. So a node is a constant, a wire of constant potential. Any region such that electrons traveling through the circuit on that region don't lose or gain energy, that's what we call a node. So when we get to superposition and you're doing these simplifications and turning on and off sources, you're going to end up seeing some wire that looks like this, and the key thing to recognize in terms of problem solving is that this whole thing can be reduced to a single node. So any line of constant energy is a node. Furthermore, right now we're talking about these as devices, and they could be just voltage sources or resistors, but eventually they could even be kind of a lumped circuit. So when we do Thevenin and Norton equivalent circuits, this entire thing could be a circuit itself, containing voltage sources and current sources and resistors, etc.
Yeah, so one of the other things we talked about earlier in the semester was series and parallel combinations, so that should also hopefully be pretty routine at this point, but the idea is if we have resistors that are in series, R1 and R2, then that is equivalent to a single resistor whose resistance is the sum of the previous two. And similarly, if we have two resistors in parallel, R1 and R2, then that's the same as a single resistor. So generally what we say is that like 1 over R equivalent equals 1 over R1 plus 1 over R2. The trickiest thing about series and parallel combinations is often just understanding exactly what constitutes a series combination or a parallel combination, right? So like we generally just think of it as like a series combination means they're on the same line or something like that, and a parallel combination means they're parallel lines in our drawing. But like, for example, if we had a network like this, right, it sort of looks at first glance like these two guys would be in parallel and these two guys would be in series. Neither of those statements is true, right? Because these two guys aren't in parallel, because to be in parallel, you need both sides, both nodes, both terminals of your device to be at the same potentials as each other. So these bottom terminals of these two resistors are at the same node, but the top guys are not, and so they're not in parallel. Similarly, for two components to be in series, they have to be just along a single branch with sort of no escape path, with no other wire coming out, with no other device coming out. And so here, it might look like they're in series, but they're not because there's this branch that goes down. However, these two resistors are in series right now. right? Just because I drew it with like this right angle here, that doesn't mean anything physically in terms of the circuit. All current going through this resistor is just going to turn and go through that one too, and so these guys would be in series. And so if we wanted to simplify this, right, these guys would be in series. We could replace them with a single resistor. And then once we have a single resistor here, that equivalent resistor would be in parallel with this guy, so we could combine those. And then these guys would be in series. So you can sometimes sort of chain them together and find the equivalent resistance of a whole network of resistors. But it's very important to just keep track of exactly what it means for two components to be in series or parallel.
So we're still on step 2, which is our basically intuitive analysis. So even though we learned a lot of more advanced techniques after this week, the techniques of like identifying series and parallel resistors and voltage dividers and current dividers are really important so that when we're applying these more techniques, we can kind of save a little time and like if we use our brain a little bit. Okay, so just a review of voltage divider. So we have a voltage source. So we have V in and we have V out. And we know intuitively when we see this, because we can derive this just from using the fact that these resistors are in series. So in particular, the resistance of the ratios. The ratio of the resistances would be R1, which is the fraction of V out that we're looking at, over the total resistance that V in sees, which is R1 plus R2. So always like commit this to memory. You should not have to apply any techniques to solve this problem. Like you should know it by heart.
Two somewhat subtle things that are important to keep in mind here are one, as Hannah drew, right, like first this was just V out. You have to add this other sort of terminal here or define a node as sort of the negative side, right? Because voltage is this differential reading, and so just saying that this is V out, it's V out relative to what? You always have to have your relative reading, and so that's when we define a ground node, which we'll get to in a minute. That's just always the universal zero for the circuit. Yeah, I think that's the second thing to note is, right, these two resistors are in series, even though there is this little branch here. The reason is this isn't connected to anything, right? This is just like an open circuit, and so no current is just going to flow into this little stub of a wire here. And so these resistors stay in series. Yes?
So is support like the opposite than like there actually is current going? Like when you look something from a support, they still deny that there is current coming into it.
So that's a really important thing to note. Is there's a big difference between when we draw something like this. So I've drawn just a wire with a plus sign, a wire with a minus sign. This means you're taking your probe and you're measuring like the voltage you get out here. Like you put your ground probe here and you took your other probe, you put it here, and you measure that voltage. That's very different than saying that there's like a voltage supply between those two terminals. Does that make sense? So if there's a voltage supply through two terminals, then current can flow through it. Like there is current flowing through this V-in source. But there is not current flowing from the minus terminal to the plus terminal in this direction. There would be current along this branch, but there is no current here. This is simply like a passive measurement you're making.
You are correct that if we were to actually attach like some other component there, some other whole circuit, then yeah, this would change things, and R2 and R1 wouldn't be in series, and this wouldn't be a perfect voltage divider. The idea is, as Hannah said, we're just measuring it. Now, even right, technically applying the scope probe is creating this whole circuit. We've designed scope probes, though, to draw like almost no current so that it doesn't really disturb whatever it's measuring.
So you can think of a scope probe as you are completing the circuit in some sense, but you're completing it with a path of infinite resistance so that no current flows through there. So effectively, there is no path. Good? Does that make sense? Okay, cool. So the dual to voltage dividers is if you have instead of a voltage source, you have a current source, and if we measure, and say we have, so it divides the current, so we'll have some current going through one path and some current going through the other. R1 and R2. Is this legible? Can people read this? Okay, thank you. So in this case, we had this nice like proportionality. So it was the ratio of what we were looking at to the total amount. In this case, we have that I1 over I is equal to the other term, so R2 over R1 plus R2. So if R1 plus R2 is like the total amount, and which kind of intuitively what's happening is if you think about like an electron traveling through this path, then it's easier for the electron to go through the I1 path if there's more resistance on the other path. So
path of least resistance, right?
Yeah,
Things
path
like
of
to go
least
through the path of least resistance. So if R1 were enormous and R2 were really small, then almost all of the current would go through R2. And that is borne out here because then, right, the amount of current I1 going through the enormous resistor would be very small since it's proportional to the other resistor.
good. So having kind of this intuitive concept in your head is important. Then you'll be able to remember these more easily. Okay, so let's go here. Okay. Yeah. So the first kind of technique you've learned in this class that is something you might, that is a little bit more complicated is nodal analysis, but also a very, very powerful tool. And what you do with nodal analysis is basically combine this methodology of solving a circuit. Like it gives you a really formal way that will always work. And it combines KCL and KVL. So when you did KCL and KVL, sometimes maybe you had too many variables and not enough equations, or you had redundant equations and you didn't really know, how to solve it, what to get rid of, that sort of thing. Nodal analysis you won't end up with a problem like that. So with node analysis, we're taking what we've defined to be a node, and we are looking at all of the currents. So nodal analysis is about summing up all the currents that go into a node, so our KCL. And I'll just say there's n currents going into this node. And at the other end of each, so what the node equation would say would be that I1 plus I2 plus to IN is equal to 0. So make sure you're consistent with the directionality. So either everything summing in is 0 or everything summing out is 0. Then what we do is we take our KCL and we add KVL. So we know that if we have two nodes and we have some node voltage on one of them, some node voltage on the other one, and we have some resistor between them, then we know the current flowing, let's say, from E2 into E1 using, is E2 minus E1 over R. So then what we do is we take this and we plug it into our KCL equation. So what this looks like when we're problem solving is we'll have some node, and we'll call it E0, and you'll have a bunch of other nodes, E1, E2, way, and maybe each one is connected with a resistor. And this is kind of just a very generic setup that you would see. And then you just go in order. So you pick your node, and then you say what are all the nodes coming that have elements going into that node, and then you just go in order applying this equation. So you would do E1 minus E0 over R1 plus E2 minus E0 over R2, etc. And that whole sum is 0. So when you're going through your circuit, and we'll go through the formal steps of this, you'll pick each node, you'll write out the node equation for that node, and each node equation kind of has one special variable. So in this case, it would be E0, which is the center, the location you applied the node equation to. And what you'll see, so we'll actually add one more step. If we add some, let's say some current source going in, we would add up, we would have I. And what you'll see when you simplify this out in terms of E0 is, and substituting for GI is 1 over Ri, so that the math is easier, we would find that G0 plus G1 times E0 plus G1, sorry, minus, oh no, I already had the minus, plus G1 R1, G1 E1 plus G2 E2, and so forth, is equal to minus I. And you'll have an equation that looks like this for every node that you apply this to. And ultimately, this will lead into something that we'll cover in a bit called the matrix method. So
Yeah, so this is just a generic matrix.
yeah.
You know, we have, a generic circuit. We have some resistors. We have some different types of independent sources, both voltage sources and current sources. So this is a great example to do nodal analysis on. So nodal analysis has just a sequence of steps. If you follow those steps, you will always be golden, and nodal analysis will always work, right? Some of the other tricks we've used for different circuits require some sort of condition to be met, right? So like Thevenin and Norton stuff requires the circuit to be linear, and we'll talk more about that later. Different things like that. Nodal analysis is always going to work for you. So the first step of nodal analysis is to just identify the nodes. So I've done that in the circuit over there. Right, so we have 5 nodes here. It's basically any location of connected wires. So, you know, there's one giant node here at the bottom, I've labeled it E5. So KVL, right, as we talked about earlier, has to do with all of these different loops. And the reason that KVL works is because voltage is this differential value. And so if you get back to your starting location, you have to have added 0. But oftentimes, instead of always sort of doing this differential stuff and going around a loop, what's easier is just to universally declare this point equals 0, and then any other point in space, we can just call it some voltage, and that is relative to the 0 point, and that's what we call ground. So the second step of nodal analysis is choose your ground.
And there's some things that make a good ground. So not all grounds are equal in terms of problem solving. They will all give you the right answer, but some of them will be easier than others. The reason this is true is your supernode, which you've covered, is a supernode occurs when you have a floating voltage source. So what is a floating voltage source? A floating voltage source would be something like, so let's say we define ground to be over here. We know the voltage at this point, because this is ground and this is, we would have minus V2 to get to E3. A floating voltage source, we do not know, we only know the relationship between the voltages on either side of the voltage source, but we can't say that the node voltage here is something at this point. So the way you want to choose your ground is such that it is connected to as many voltage sources as possible, because then the first step of your problem solving, or I guess it would be like the fourth, would be you would be able to actually identify what the node voltage is around those voltage sources if they're connected to ground. So if we choose this to be ground, we could say what E3 is, but if we had not chosen this to be ground, if we had chosen ground to be over here, we would not be able to label immediately either of these. So it's a tool for problem solving, which is choosing your good ground.
Right, so after you've chosen your ground, then you do want to identify if you have any floating voltage sources. One thing to note is current sources aren't really involved in this. You don't need to worry about floating current sources. A supernode is when you just have a floating voltage source in particular.
And the reason you don't have to worry about current sources is that when we did this method, this technique, the point was we were representing a sum of currents. Like, it all came from our KCL. And when you have a current source, you know the current going into the node that the current source is attached to, because it's just whatever the current from the current source is. But if you have a voltage source, you don't know the current going through. So we had that, if we had drawn the IV characteristic of your voltage source, it would look something like this. So you would have some voltage, but that voltage could exist for any current. So that's why we don't want to involve the floating voltage sources, because we don't know the current, so we don't know how to involve it in this equation.
Right, so one thing to note about this circuit is there's no choice of ground that will allow you to avoid supernodes, right, because we have these two independent voltage sources and there's no node that's connected to both of them. So your best bet is to just choose some node for your ground that's connected to one of them. It's often intuitive just to sort of choose the bottom of your circuit as ground, just because that's often how we draw them, and it is good practice to draw it that way just because it's easier intuitively. But from a mathematical standpoint, E1 would have been an equally good choice for ground as E5 would be. All of our specific node voltages, so like E3, E4, E2, those would all turn out to be different values depending on what we chose our ground to be, because they're all referenced to ground. But when we ultimately solved for the voltage drop across any component in our circuit, or if we were actually solving for the current through any branch, that would all turn out to be the same regardless of what ground we chose. So having chosen a ground node, the next step is to label all the potentials. So we've already labeled the ones that are unknown, but choosing a ground allows us to know some. So like E5 we can get rid of because it's just now ground, it's 0. We also, as Hannah said, we now know E3. It's just going to be negative V2.
Is everyone comfortable with the negative sign there?
And then, right, we see that we have this supernode here. So the way we deal with this supernode is that we kind of want to view it as 1, so I'm going to get rid of E4 and leave E1. And then what we do is we view this really as a single node. It's just a bigger node because it has this voltage source stuffed inside it. And the idea is, the reason why we can do that, to treat it as one node, is, right, the whole idea behind KCL is that there's never going to be a buildup of current at some point. But there's also not going to be a buildup of current in some region, right? So if we look at the current going into this dotted circle here, it's going to add up to 0. I could, arbitrarily box in like any section of the circuit, and the sum of all of the currents going in or out of it is going to be 0. What's special about the supernode, though, is that generally, right, we have E1 on one side. We know that this side is E1 plus V1 because of this voltage source. And so then when we want to analyze what all the different currents are, we have to be careful sort of which side of the supernode we're looking at, because on this side the potential is E1, and on this side it's E1 plus V1. But in terms of sort of how many different nodes you have, or how many different node equations you have, this all counts as one giant supernode. So once we've done all of that, then the next step is to write out the node equations. So Hannah was explaining this before. For this circuit in particular, right, we just have these two nodes that we have to worry about. We have our giant supernode, and then we have E2. Let's start with E2, just because it's a standard node. So at E2, right, the first thing is how many different sources of current do we have going into this node? So we have this independent, current source. So that's going to be I0. We have this resistor, and we have this resistor. So one thing to note is you have to be very careful with your direction, like we were talking about before. You either have to add up all of the currents going into the node, or add up all of the currents coming out of the node. So when I declare that I'm going to start my equation with I naught being positive, that implicitly decides that I'm choosing to add up all of the currents going into the node. So now, when I look at these two branches and figure out what current I'm going to be adding onto this equation, I have to view it in the direction going into the node. So I'm going to be going like that. And so as Hannah was saying earlier, right, what is the current going through this resistor R1? Well, it's going to be the voltage drop across R1 divided by the resistance R1. And as we were talking about before, because the current's going this way, we kind of have to view the positive side of the resistor over here and the negative side over there, so that we have our directionality in check. And so this side is at ground, so that's going to be 0. This side is at E2, so 0 minus E2 is now the positive voltage drop across R1. And when I say positive, I don't mean that numerically this will be positive. It very well could not be. It is positive in the sense of that is the positive directionality of the voltage as we have defined it for this resistor. Does that make sense? Because that is confusing. It's just arbitrary. It's how we're talking about the circuit. It has nothing to do with the real life parameters of the circuit.
So you very well could have decided you wanted to sum up the node equation as having all currents going out of the node. And that would be also fine, but just make sure you're consistent. So pick a direction and make sure you stick with it. So either everything goes in, everything goes out.
And one trick for doing that we'll see in a second. So right, this is the voltage drop across R1, and then we have to divide by R1 to get the current through R1. And then the last branch of current we have here, we're going to do again, this would be the positive side and this would be the negative side since the current's going that way. So on the positive side we have E1 plus V1. And on the negative side, we have E2 over R2. I apologize, this is getting cramped. That is going to equal 0, right? Because that's a KCL equation. We've added up all of the current going into a node, so it adds up to 0. So one good sanity check to see if you're doing things consistently in terms of the direction of your current is that whenever you have terms like this that involve the actual node potential that you're writing the equation at, that one should always have the same sign. So in this term we subtracted E2, and in this term we subtracted E2. It would be a bad sign if in one of the terms you were adding E2 and in the other term you were subtracting E2. One other thing to keep in mind, it is easy to think that when we say, like, we're writing the equation for this node, that you're writing an equation, this node E2 equals something. That isn't what it means. The point is that we're writing KCL equations centered around different nodes. Right? Neither side of the equation is just E2 equals some expression. Okay, so that was E2. Now we have to do the slightly more complicated supernode. So it works the exact same way, it's just you have to be careful in terms of which side you're looking at because the potential is going to change. So with this node, let's do going out of the node just to see how that works. So right, we still have 3 branches that are coming into this supernode. And so if we look at this current, right, it's going to be the same term as this because we already looked at that current. But now, right, we're starting here and we're going out. So we're going to have, right, E1 plus V1 minus E2, that's the voltage drop across R2, over R2. That's going to be this current. Now, when we look at this branch, we also have to be going out of the supernode, and so we have to start here and go down. So that means that, start at the top. So our current is going to go downwards. So now, we're not going to say E1 plus V1, like we did before, because this resistor is connected to this side of the supernode. So we're just going to say plus E1 over R3. And then we have one term left. Also, we have to be going out. And so, right, positive and negative. So that's also at the E1 side of the supernode. And so we're going to have plus E1. And then we have to do minus this voltage. This voltage is negative V2. So we're going to get a minus negative V2, and yes, we can just say plus V2, divided by this resistance R4. And that, too, is going to equal 0. And one thing to note here is, right, there are only two unknowns in this circuit. Presumably you've been given all of these resistance values and you know what the values of V1, V2, and I naught are. And there are only two nodes here, right, other than the ground. And so we now have two equations and two unknowns, and that can then just be solved by, you know, substitution or elimination or however you want to do it. As Hannah was talking about before, it's often messy to just have all of these fractions, all of these terms with, you know, resistances being divided and all of that. And so oftentimes it becomes easier to just talk about the fact that, right, the conductance equals 1 over the resistance. And so, right, we could replace over R4 with just times G4, and this would turn into E1 times G3. This would be E1 plus V1 minus E2 all times G2. And that would allow you to write an equation that would have no fractions, and that could simplify and then be put into a large matrix that would describe the entire nodal analysis of the circuit.
So you have two equations, two variables, and we know we can solve this, and there's two ways you can do that. One is direct substitution. The other is this matrix method that I started to write up here. So we'll take this specific example we have and rewrite it. So this is just the first equation that Jacob derived. And if we rearrange it, so we'll try and write it as like something in terms of E1, E2, E3, and we'll like list out all of our variables. So in this case, we would have minus, and I'm going to replace r's with 1 over r with g. So we would have minus g1 e1, and we would have minus g2 e2. We will have plus g2 E1, and on the right-hand side we have minus I naught. I think that's, check this. And then if we combine these terms, oh, this should be minus.
You need the
Yes. So this is equal to minus G2 V1 plus minus I naught. Okay, so if we group terms, we'll have G1, and then I'm multiplying by -1, G1 plus G2 times E1 minus G2 times E2, multiplying, yes. This should be a plus. This is minus. This should be a plus. This should, yeah, okay. And this is equal to,
this is an E2.
yeah.
So that's probably right there.
Yeah.
And then that's
Yeah. Okay. Thank you. So this is this
that first should be
minus.
E2.
Wait, this one should be.
Yeah,
This
that
is
should be
right.
E2. The second one should be
Yes. Yes. Okay. Okay. The problem was I was trying to use what I already knew that the answer should be, but we were playing it at a different note, so I was getting the opposite thing. But if you actually do this correctly, thank you, Jacob, then you should get this. And now, similarly, we take the other equation.
I can do it
Oh,
right below.
yeah, that sounds good.
Right, so like, we're gonna replace the 1 over R2 with the G2, and then we get E1 plus V1 minus E2, and we have plus G3 E1 plus G4 E1 plus V2 equals 0. And right, then we can combine all of the terms that involve E1, all of the terms that involve E2, and then we also have these sort of independent terms, the V1 here and the V2 there, and so those are going to move to the other side. And so the point is, we're always going to get some linear equation, where we have some coefficient, generally in terms of these conductances G, in front of each of the different node potentials, E1, E2, E3, dot, dot, dot. And that will equal some combination of the independent sources around your circuit. And so once you have all of your node equations written in that way, then you can write the entire thing as one matrix, right? Because all of the left-hand sides of your equations are just linear combinations of E1, E2, E3, dot, dot, dot. And the right-hand sides are these known values in terms of your independent voltage and current sources.
So ultimately, you'll end up with some system of equations in terms of the nodes. So what this, so for this example, it was just something times E1 plus something times E2 equals something. And the things over here were involving V and I.
And are therefore known constants, right? You know V and I.
Those are your independent sources. And the second equation was similar with different constants. And then what we're able to do with the matrix method is recognize that we can solve this by using a matrix. So we end up, I'll just write some constants in here. And you would be able to say your matrix looks like this. You have some vector E1, E2 of your node voltages, and I'll give these constants E and F. So it might happen that you'll be asked to give this matrix, which is the conductance matrix. And these are your unknown node voltages that you're solving for, and these are your independent sources. So kind of in line with what we started with up here is it turns out you can actually go directly to the conductance matrix just by inspecting the circuit. So what we were seeing in our equation here when we had the sum of like our G1 and G2 times E2 and minus G2 here, we actually will end up with that form in our conductance matrix. So you can solve that out. Come ask me at the end if you want to see like what the formal derivation of what like the most general conductance matrix is. We won't go through that now, but you can go through a process like this.
So one other thing, yeah. Okay.
Okay.
Any other questions at the moment? Yeah.
So for the right side, for the independent sources, if you have like the conductance value times like an independent voltage source value, then you would put the conductance times that voltage source in the right side, right?
Yeah, and I didn't include it up here. So here I just looked at the general form if you had a current source, and I didn't include a voltage source. If you were going to include a voltage source in your general derivation, you would need to do something that looks similar to a supernode. But yeah, that's right. You have to be a little careful with what conductance you multiply that voltage source by. Yeah, does that? Yeah, come talk to me after.
Yeah, also just to note, like only the left-hand side is like the list of coefficients times E1 and E2. Like the right-hand side, you just have a single vector. You don't have this, conductances times some separate vector of independent voltage sources or anything like that.
Any questions on this? Okay, so one of the main takeaways, so this is good for two reasons. One, you can just plug this into a computer and it will solve it. So this is how circuit solvers work, and you no longer have to do really any work in simple cases. The other thing that this is useful is it tells us that our circuit is linear. So this is going to take us right into linearity and superposition.
Yeah, so one thing you might have noticed and perhaps thought of is that, right, we have these three different independent sources in this matrix. And so this matrix would be a prime candidate for solving using superposition. Clearly, we did it just fine with nodal analysis. It didn't take too long, but you could totally solve this with superposition, right? And so for superposition, you would turn off all but one independent sources at a time and solve the circuit with just one independent source on at a time, and do all three of them in this case, and then add up your results at any specific node you were solving for. What's nice about superposition, especially in a case like this, is that when you turn things off, often the circuit becomes a lot simpler. So like for example, when we turn off the two voltage sources, right, when you turn off a voltage source, it becomes just a wire, becomes a short circuit. And so now all of a sudden we just have this current source and then this whole network of resistors. And as we were talking about before, right, R3 and R4 are going to be in parallel once this is just a wire because they share this node and they also share this node. So these guys will combine and then they'll be in series with this and parallel with this. The circuit's going to simplify a lot. When you turn off an independent current source, it does the opposite. Instead of becoming a wire, it just becomes an open circuit. So you can basically just like eliminate it from your circuit. You would just like get rid of this entire thing. Yep. And the intuition behind that, it makes a lot of sense. When we say that we turn off a source, it really means that we set its value to 0. So for a voltage source, we would be setting it to 0 volts. For a current source, we'd be setting it to 0 amps. And right, if you think about it, what does it mean for a voltage source to enforce 0 volts will drop across me, right? What circuit device that we use all the time in every circuit we've ever built has 0 voltage dropping across it? That's a wire, right? That's how we define a single node. It's where we just have all wires connected. There's no voltage dropping anywhere. And so that's why a voltage source being turned off, set to 0, turns into a wire. Alternatively, a current source being set to 0 means that it is enforcing no current will flow through me. Well, what circuit device doesn't flow current through it? An open circuit, right? Just like air. And so that's why they simplified this, and that's good intuition to keep track of in case you forget, which turns into what.
Okay, and we'll go through the analysis of this after we cover superposition more formally. Okay, so as I was saying, this algebra that we just did shows us our circuit is linear, and this happens when the elements in your circuit are linear. So V equals IR, that's linear. So the second thing we learned from this is if we were to solve this equation, we would get E1, E2, something, 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 and we would have some constants in front of it. So it would look like A1 times 2. Does that kind of make sense? So when you solve a linear equation, you get a linear solution. So in particular, each node voltage is going to be expressed in terms of all the other node voltages. Sorry, what am I saying? These are your sources. So we multiplied it to the other side, and up here are our current sources and our voltage sources. So this is going to look like A1 times I1, A2 times I2, B1 times V1 plus B2 times V2, and something like that. Does that make sense? Sorry for the error. So we take this matrix, we invert it, we express a solution for E1 through En in terms of this matrix that only involves resistor values, so those are all just constants. And these are our voltage sources, so E and F are going to be some combination of the variables I and V, where those are our independent sources. And so when we do that matrix multiplication, we're going to end up with some sort of thing that looks like this.
And the key here in terms of being linear, we're not multiplying any of the different independent source values together. Like you're never going to have I1 squared or I1 times I2 or I1 times V2 or V1 squared or anything like that. All of them are just going to show up as their own terms with constant coefficients. One other thing to note is just that the A's and the B's here have different units, right? It wouldn't make sense to add a voltage to a current. So because we're solving for voltages, all of the B's will just be numbers, no units, whereas all of the A's will have units of ohms, right? Like resistance times current equals voltages.
Questions? Okay, so this is actually really important. I'm gonna get rid of this part, and we're just gonna say we were looking at one node variable, so E1. Thank you. So what does that mean? Well, we have some sort of circuit, and let's say our circuit is in here, and we were looking at one point, and this node voltage, let's say this was ground, and we were looking at, say E1 was at this point in the circuit. So what that means is like, here's ground, here's E1, and then we just push the rest of the circuit to one side, and we're left with E1. And we have an expression for E1 in terms of the independent sources in our circuit. Does that make sense, what we're doing? Okay, so now this is where we get to superposition. So what the nodal method did and what the matrix method showed us was that we could express E1 in terms of a linear sum of all the things going on in the circuit. So in the circuit, you have some current sources, and you have some voltage sources. And then you have all the resistors connecting them. But recall, the resistors are all in here. Okay, so then what you can do is you can say, well, E1 is the sum of these things. So E1 is the sum of just that. E1 is the sum of just this term. It's the sum of all those individual terms. And what that means is we can say E1 is the sum of the circuit with just this element, the circuit with just this element, et cetera, with just its element and just this element. And that's what we're doing when we do superposition, is we're saying we turn off all of the sources, i.e. we set all of these variables to 0, except for the one that we're looking at. And so that goes back to what Jacob was saying, is what does it mean to turn off a source? What does it mean to set one of these variables, these independent sources, to 0? That means to turn it off. That means if it's a current source, you would redraw your circuit with that element being an open, and you would draw that voltage source being a short. Does that make sense? Okay, so now we're gonna do this with this circuit. Do you wanna?
Yeah, so, right, so if we turn off V2 and V1 for a moment, so we'll remember that these are here, but
Do we wanna read? We could redraw.
I think it'll
Okay.
work out. So first, we're just left with this current source. And as I was saying before, right now these two resistors are in parallel with each other because they share this terminal and they share that terminal. So we get, R3 in parallel with R4. That then is in series with R2, right? If we were to redraw this, I don't want to get rid of anything. Right, if we were to redraw that part of the circuit, we would basically have this current source, I0. We would have R2, and then we'd now have this combined equivalent resistance. This would be R3 in parallel with R4, and we would use our equation from earlier about combining parallel resistors. And now these two resistors are in series, right, because they're just in this one branch. And so now we can replace that with a single resistor where we've added R2 into the mix. So now this just becomes this guy plus R2 since they were in series. But now, as you may have noticed, these guys are in parallel, and so now we can just get rid of this guy. Put that whole thing in parallel with R1, and now this is a very simple circuit. So like, for example, if we were solving for, some specific spot in the circuit as our output voltage, so like if we were solving for like E2, say, E2 stayed put. E2 is still at the top of this current source, and so now it would be pretty easy to figure out what E2 is. We have this current I0 flowing through this single resistor, quote unquote, and so the voltage is just I0 times that mess of a resistance. One thing to note, though, that is important to keep track of, if you were trying to solve for like E1 or something like that, E1 kind of got swallowed in that combination of all of the resistors. And so it is important to keep track of, you can't just like get rid of everything and then just assume that the node you're left with is the node you were originally looking for. You do need to keep track of where all of the different nodes sort of got collapsed in as you were combining resistors. But clearly superposition makes the analysis a lot easier to do.
So as you might have done that for the DAC problem, that was one of the labs and also one of the homeworks, but something you could have done if you were doing this is just keep track of things as you're collapsing them, so represent E1 in terms of E2 when you do that thing.
Yeah, and then, to solve the full circuit, then we would,
reintroduce, take this, yeah, this was, but that was V2, upside down. Right, so we would add in this guy. This guy's still off, and now this would just become an open. So we just get rid of this altogether. This is also a straightforward circuit to solve because, again, we just have all of these different, this was not a wire. We just have all of these different resistors in series and parallel, and we would do the same thing. Once we had our results from each of those different solutions, we would basically add up things together. So like if we got some formula for E2 here in this circuit now, we would add our formula for E2 from this circuit to our formula over here for E2, and then we would get our third equation for E2 from the third, where we just left on this voltage source, turned this guy off. And if we add all of those together, we're going to get the total formula for E2 because we basically set this to 0 and that to 0 and been left with this term. We set all of those to 0 and got this term. We got each of the terms one at a time, and so we have to add them up at the end.
So when we're doing this, when we're turning off sources, what we're computing is not actually like the full E2, or if this were E2, so let's say that's E2. We're not computing the full E2 when we look at the partial circuit. What we've computed is some partial term. We've computed something on the right-hand side, and we found the contribution that that term has to the full E2. Does that make sense? So that's why you can add these circuits together. Okay, so that leads us into the next. Is it okay to erase this? Okay. So that leads us into the next topic, which is our circuit equivalence. So we kind of started to do that up here when we were looking at this lump of circuits, and we knew that we could express the node voltage in terms of this linear combination. And we can do something a little bit more general to really characterize a circuit. So I'm going to draw that again. Here's our kind of abstract circuit lump. And now we have these terminals coming out. And we have voltage sources and current sources in here, and some network of resistors.
Right, this has to be linear.
Linear, yes. And why does everything have to be linear in there? Well, when we did the derivation using the matrix method, you can only get there if everything is linear in the first place. Okay, any questions about that? So if something weren't linear, then you would end up, instead of with an expression where you have one term times I1, one I2, and they're all separate, you would have something that was like maybe I1 squared, or like, 1 over I1, or something like that, or maybe even I1 times V2. So it's possible that you have sources that aren't simply like, yeah.
One thing you can think of, right, like we've talked about IV curves, and so like a resistor is like some diagonal line through the origin, voltage and current source are just like straight horizontal or vertical lines. You could imagine some device that has an IV curve, some like crazy exponential or quadratic or like whatever. There are devices like that, and so those would be nonlinear devices.
Yeah. So like if everything is a line and you sum them all together in some way, like some scalar multiple of all these lines, you're still going to get a line, kind of intuitively. If you have something that's not a line, then it would be.
Yeah.
So an RC circuit at time equals 0 counts linear.
We will get to that after. So a capacitor is not a really linear device. And we'll talk about how to deal with circuits involving that. So right now, these are things for which like the voltage is proportional to the current. So anything that you can draw on an I versus V plot.
If it's a straight line, then it's linear.
Yeah.
Right, and capacitors have to do with like the derivative of, right, the...
I'm just thinking because at time equals 0, you can treat the capacitor as like short. So,
Yeah, correct. So there are like models that we use for capacitors at different points in time that reduce to simplified linear models. But like in general, if you're analyzing a circuit with a capacitor in it, you're not gonna do this. Sometimes what you do is you'd sort of take the capacitor out and analyze the rest of the circuit, because that would be linear, but the capacitor itself is harder to deal with, and we'll get to that later.
Yeah, and we actually will come to a technique that does work for capacitors that brings all that we've discussed back again. Any other questions about this? Okay, so, and a point to note is, like, even when you have, like, whatever you have in your circuit, like KCL, KVL, and the nodal method will always work. It's just that when you go to the matrix from the nodal method, it only works if everything is linear. Okay, so we have this, like, abstract linear device, and we want to characterize its behavior. Like, it's a black box. And so you could go to a lab, and you could try to characterize this yourself. You could, if I have an IV curve, you could send a current through and then measure the voltage, and you could do this for every single possible current point. You could do this for, or you could do the opposite, which would be apply a voltage and measure the current, and you could do that for every point, and you would get some characterization of what this circuit looks like. So it turns out if this circuit is linear, you don't need to actually take it to a lab and do that, although you could. We have a way to do that ourselves and calculate that. So we'll start with the first method. And does that kind of make sense, like why you're characterizing the circuit by doing that? Like, we just want to know how I relates to V. Like, if we're going to use this device and attach it to something else, all we care about is what is the voltage response for a certain current, or what is the current response for a certain voltage. We don't care about anything in here. Yes? Okay. So let's start with the first of those options, which is, actually, I'll start with the other. It wasn't this. So let's start with this one. So we're going to send in a current to our black box, and we're going to measure the voltage we get out. So I'm going to write V, and I'm going to call this some V test, and this is really like our response. Just ground this, and this is I test. Okay. So what we're doing is we'll just apply this linearity or the superposition, whatever it is, but we know that ultimately we're going to be able to say that V test equals, it's proportional to our first current source, so some A1 times I1. It's proportional to our second current source, so some A2 times I2, etc. It's proportional to our first voltage source, so some B1 times V1, to our second voltage source, B2 times V2, etc. And there's one last thing that we've missed. So we've now added all of the independent sources that are in here. There's one more thing, which is the current that's out here. So this is a source. This is the test source we're giving our circuit. So there's one more thing, and that is some constant C times I test. And now what we're doing is saying we don't actually care. Remember, we don't care about any of this. We don't care about that. We just care about the ultimate relationship between V test and I test. So what we'll do is we'll just group these terms together. And we're going to call this term, we're going to define that to be V Thevenin. Similarly, we're going to call this constant for I test, we're going to call that R Thevenin. So when you see a Thevenin voltage and a Thevenin resistance, what that really is saying is we had some big circuit and we didn't care what was in there, and we're just kind of trying to summarize it. And what this allows us to do is, thank you. So what that equation leads to is the following, where we say V test equals V Thevenin plus R Thevenin times I test. And now, instead of this big, weird circuit, we can write what we call the Thevenin equivalent circuit. So that would look like this. We have a voltage source, V Thevenin, we have a resistor, R Thevenin, and we have our output terminals where we were measuring where we sent in our eye test and where we measured V-test. So if you see, this circuit is the same as this equation. So the value at V-test is our voltage source plus the voltage you gain from this point to this point, which is R Thevenin times I test. So instead of talking about some giant circuit with a bunch of current sources and a bunch of voltage sources and resistors, we can simplify it and talk about our Thevenin equivalent circuit. And so ultimately, our Thevenin equivalent circuit, we don't include the I test, we just write it as this.
Right, the I test was just a mechanism we were using to determine the values of V Thevenin and R Thevenin, but fundamentally the idea is that this entire mess of a circuit, whatever's in here, is equivalent, as far as we are concerned, to this, just a single voltage source in series with the resistor. And that can make your analysis a lot easier if you can simplify an enormous circuit like this. You can also do sort of the opposite idea. So, right, you can apply V-test and then you would measure I-test, and that is flowing in, right? We always say that we have our current flowing into the positive terminal of the device. So in this case, this entire blob is our device. And so since we have the plus side up here and the minus sign down here, I-test is going to be flowing into this positive terminal and come back out the negative terminal. And so when we do it this way, the same principle applies, right? The response we're going to get, this current we're going to get, is going to be proportional to all of those independent sources inside the circuit, just like V-test was before. One thing to note is now, right, the A's are going to be unitless because we're solving for current, whereas the B's now are going to have units of conductance so that we're converting voltage to current. Nonetheless, we're going to get this response in terms of the actual circuit itself, plus some relation to V-test. And now, because, right, I-test and V-test are switched, now this is going to be sort of like 1 over R, and now we're doing normal. And so the idea behind that is that now, instead of a voltage source in series with a resistor, we can also express the circuit in terms of a current source, the Norton current, in parallel with the Norton resistance. And it yields the equation that Hannah's just written. And one thing to note, which is very helpful, is that RTH and RN, the Thevenin and Norton resistances, are the same. Now, at first glance, that might seem like some happy miracle. You know, how did that end up working out? And if you think about sort of the idea of what a linear circuit and how we're modeling it means, it actually makes a lot of sense. Right? We were talking earlier about the fact that you're always going to have some IV curve for whatever circuit you're working with. And the idea of a linear circuit is that it's going to be some sort of straight line, whatever that is. And, right, this kind of looks like a resistor, right? Like a resistor would have some diagonal line. The fundamental difference, though, is that for a resistor, it has to go through the origin, right? If you apply 0 volts across a resistor, you're getting 0 current and vice versa. With an arbitrary circuit like this, you might not be, right? If this were like, you know, just a voltage source, for example, it certainly wouldn't go through the origin. It would just be some, you know, horizontal line. But the point is, we can model this linear circuit in terms of its IV characteristic, which is some straight line. If we look at the slope of this line, that essentially becomes this C value, right? That's the slope because that's how our I test and our V test were related to one another. Since this is I versus V, this slope is 1 over RTH and 1 over RN. And then the offsets from the origin have to do with V Thevenin and I Norton. So this intercept here is V Thevenin. This intercept here is minus IN. very important to remember the minus sign. And the idea behind that is, right, this is the IV curve. So where we intersect the I-axis is when V equals 0. So like if V were to equal 0 here, right, these would be at the same voltage. There would be no current going through the resistor. And so I test would be facing in the opposite direction of IN, which is why our I test is the negative of the Norton current. But yeah, it's key to remember. You intersect the V axis at the Thevenin voltage, the current axis at the negative of the Norton current.
And I'll add this back, sorry for erasing that. So we end up with these two simplified models. And this one had equation V test is VTH plus IRTH. So we have our Norton equivalent circuit up here, our Thevenin equivalent circuit over here. Thanks. And the reason this is really useful is now if we want to solve a problem, we don't have to think about everything that's in that blob. We can just replace that part of our circuit from which we've computed the R Thevenin and V Thevenin, or Norton equivalents, and we can just replace it with one of these two models. And you might wonder, like, you know, when would you want to replace it with this one? When would you want to replace it with this one? It depends on your problem. So the nice thing about the Norton equivalent is that when we do nodal analysis, it's easy to deal with current sources. Plugging that into your circuit would be fairly easy for that kind of analysis, whereas V Thevenin, it's possible it would become like a floating voltage source if you plug it into the rest of your circuit. So those are just things to think about. But these are equivalent. You can use either for the rest of your problem solving. And when we get to RC circuits, we'll find that we want to use this one, and this helps us compute things like the time constant. But we'll get there soon. So we're moving on to dependent sources now. Yes.
Just a quick question on that. So, like, you compressed everything by seeing what things were up there, like what things were in parallel and series with each other.
Yeah.
When you need to find like the equation for the node, do you have to re-expand? Because there were like E2 and E3 and things like that.
Yeah, so if you wanted to get like what E1 and E3 were out of this, right, it doesn't exist in this current model of the circuit. So one thing you could do, right, is you could like break it down like this, solve for E2, and then slowly expand back out because you now know the value of E2. As Hannah mentioned, you can also sort of keep track of the nodes that you're consuming as you're going. So like for example, right, if I had a resistor and a resistor, this were ground, and this went to the rest of the circuit, say that this were E2 and this were E1. These resistors are in series, right? And so what I would want to do is turn them into, you know, a single resistor. And this would then be E2, right? But if I wanted to keep track of what E1 was, well, this is like a voltage divider like we talked about earlier. So I could say right here that E1 equals E2 times R2 over R1 plus R2. So now I don't need to keep E1 around anymore in my circuit, because then when I eventually solve for E2, I can just plug in for E1. And then I might have expressed E2 in terms of E3 because I consumed it and so on and so forth, but you can keep track of all of them as you're going.
Thank you.
Yep.
Any questions about anything we've done before we move on to dependent sources?
If we switch from Thevenin to Norton, how do we know which way the current is flowing?
Yeah, so going back to what Jacob was talking about and reinforcing in the beginning, it's all just how the normal way of defining it. So the way we've defined the Norton equivalent circuit is the Norton current goes this way, and again, with how we defined how we look at a device with like the plus terminal, minus terminal, and current going into the device, that's the same thing here. So when we do these IV characterizations, it's always the current is going into what we would call the plus terminal and the minus terminal. What we've defined to be the plus terminal and minus terminal. So if you look at this circuit, you'll see that the way we need to define the Norton current is such that it has to be negative, so that like if you define the circuit like this, then when you get the equation, you get this negative sign here. Does that make sense?
Like for example, if we were to define, right, I test going down, like we could, then, right, I test would end up being in the same direction as IN. So we would get, you know, I test equals positive IN, and then it would be like minus V test over RTH and stuff like that. It's all about the self-consistency, as Hannah was saying.
So definition is I test always goes into the plus terminal, out of the minus terminal.
Anything else?
Okay.
Okay.
So dependent sources. The good thing is most of what we've covered is pretty much the same. So in particular, if we're using dependent sources that are linear, then our superposition, I'll just write it out. So superposition and Thevenin and Norton are the same. Nodal analysis always will work. Any case, nodal analysis will always work. If we have a dependent source and we want to use superposition or Thevenin or Norton, then it has to be linear.
And what that means linear, right, the idea of a dependent source is that it's either a voltage source or a current source, but the value of that voltage or current source is some function of some other parameter in your circuit, right? So oftentimes you'll have like a current source and that equals like beta times some other voltage in your circuit. Hypothetically, we could give you a dependent source which would be like beta times V squared for some V in your circuit. That would no longer be linear. And so you could use nodal analysis as always. You couldn't use, you know, these other tools that we have because it's no longer linear.
Okay.
When you do superposition or Thevenin or Norton and stuff, you only turn off though the independent sources. You never turn off a dependent source. That always stays. And if you're doing Thevenin or Norton, if you're sort of consuming the dependent source into your black box that you're modeling, whatever parameter it is defined in terms of, right, if it's beta times some voltage, that voltage also has to be inside the black box that you're modeling. You can't split up the dependent source from what it's dependent on.
And the reason we don't turn off the independent sources goes back to how we kind of came up with the method of superposition in the first place, which is that all of these things are things we have the ability to set to zero. So they were independent. We could turn them off and we could look at the circuit as a sum of those individual components. But if something depends on one of those, then you won't know like how it will react. So you want to just leave it there and it will respond to turning off the independent sources. Okay.
Now,
Yeah.
dependent source.
Yeah. Let's see.
We will get back to dependent sources a little bit because it'll become relevant again in a second. Does anybody have any immediate questions about them? Okay. One other thing that we've covered more recently is op-amps, right? These mysterious devices. So let's swap here. Right, so an op-amp is a differential amplifier. It has the two input terminals, V plus and V minus, and then it has the output. And the output is some scaled version of the difference between the two inputs, right? It's like A times V plus minus V minus.
And something you'll remember from lab is that the output of an op-amp, in reality, it is powered by something, so your rails that we don't normally draw. And mathematically, the output is defined by this, but physically, the output can only be between the low rail and the high rail. So if it's higher than the high rail, it will cap at that, and if it's lower than the low rail, it will cap at that.
Right, so one key to op-amps is that A is generally enormous. We like to think of it as infinite. In practice, it is not infinite, but it is very, very large. And so, right, the problem we would run into is, right, if A is like huge, if A is like 1,000,000 or something, and V plus minus V minus were like a volt, we would be trying to get 1,000,000 volts at the output, and as Hannah said, it would just cap to whatever our highest voltage power supply was. So that's not, particularly useful, at least as far as we are currently concerned. And so often what we do is we employ what's called negative feedback. And the idea is that negative feedback sort of keeps an op-amp in check. It prevents it from sort of growing unboundedly and capping out, or going down unboundedly and capping out until it reaches power rail. And so the idea is that we have some path. This can be anything. It can be a resistor. It can be some complicated network of resistors. It could just be a wire, whatever it is, back to V minus. And the idea is this, right? In order to make this something reasonable, something not absolutely enormous, since A is, for all intents and purposes, infinite, the only way we're going to get something finite at V out is if this is 0. Right? 0 times infinity, these are just abstractions, but the idea is that V plus minus V minus is going to be really, really small. And so that's why when we're working with an ideal op-amp, we say that V plus equals V minus, right? And so what you can imagine is if we had a circuit like this, and V plus equaled V minus, so we were all set, and V out, let's just, for real simplicity, let's just make this a wire. So V out is going to equal V minus, which equals V plus. Imagine there's like a little bit of noise in your system. So imagine that V plus gets like a little bit bigger. And so now all of a sudden, V plus minus V minus is positive. And so V out is going to be wanting to multiply this positive number by its huge amount. And so V out is going to start rising. What happens when V out starts rising? Well, since it's tied to V minus starts rising too. And it rises until it's reached V plus. And now this is back to 0 and we've stabilized again. And so by tying that output back to the negative terminal of the input, we kind of do this self-correction mechanism that prevents it from getting unbounded. If we were to have positive feedback, the opposite thing would happen. If we got a little bit off center, then it would exponentially shove itself further and further off center, and it would be really, really unstable. So if you're looking at a problem that we've given you with op-amps, first thing to check, have we said this is an ideal op-amp? And second, you're looking for negative feedback, and those will often be done in the same problems. In addition to the V plus equals V minus, when we talk about ideal op-amps, one other very important ideality is that we say that I plus equals I minus equals 0, where I plus is the current going into the positive terminal and I minus is the current going into the negative terminal. The idea being that this side of the op-amp draws no current. However, the output can supply current. And right, at first glance you might be thinking, like, does this violate KCL, right? This component, it has no current coming in this side and then it has all this current coming out that side. The reason it doesn't is what Hannah was saying before. We do have these power rails that we don't usually draw because they're just implicitly assumed to be there. But that is where the current would be coming in that can then come out the output.
Okay. Any questions about this? And then we're going to do a problem involving op-amps and dependent sources. Okay. And one last thing to note about problem solving, because there's some amount of current coming out, and you don't know what that current is, just like when you were solving the original problems earlier with a voltage source, in particular a floating voltage source, when we were doing nodal analysis on a problem with a voltage source, a floating voltage source, we didn't know what the current through that voltage element was. And it's a similar thing going on here. We don't know what the current coming into or out of this node is. So when you're applying the nodal analysis method to something involving an op-amp, this will always end up being involved as a supernode. Does that make sense? Okay.
All right. So one common thing to do with an op-amp is to make some sort of amplifier. And so the idea is if we have some input voltage and we want to scale it by some fixed amount to get our output voltage, we can sort of set resistors up alongside the op-amp and it'll do the work for us. Op-amps can also do a lot of other crazy or cool things. They can, add, subtract, they can differentiate and integrate, believe it or not. It's very cool stuff. We will get to that soon in the class. But, one thing that we can do, if we have our op-amp here, then if we inverting or non-inverting?
So if we have like a very basic setup with resistors, there are two things we can do in terms of where our signal is and where our ground is.
Right, so this would be an inverting op-amp configuration. This would be R1 and R2. Right, so this positive terminal we've set to ground. This negative terminal has VN through this network of resistors. And so if we were to say that this is an ideal op-amp, the first thing to note is we do have our negative feedback, so that's good. If this is an ideal op-amp, what we notice is, well, we know that V plus equals V minus, right? So if this is ground, then this is also at 0 volts. This is called virtual ground. And so that's 0 volts. What we also see is that there's no current going into the negative terminal, right? That's one of our other ideal op-amp assumptions. And so that means that all of the current going through resistor R1 isn't going to go here. It's just going to go down and go to resistor R2. And so those resistors are kind of in series with one another. All of the current's just going to go through the full range. And so, if we define our current going this way, we know from this piece that, V in equals I times R1, since this current drops across R1 gets us from V in to 0. But then that exact same current is going to go through R2. And so if we want to know what V out is, it's going to be negative I times R2. The reason I said negative I is because now the current is flowing from 0 volts to V out, right? So we'd really be getting like 0 minus V out equals a positive value. But now we can say that I is V in over R1. So we get minus V in R2 over R1. So this is called an inverting op-amp because we have this negative sign here. V out is proportional to the negative of V in. Generally, we don't really care about that. What we care more about is sort of the magnitude of the output. And the scale factor, R2 over R1, allows us to choose whatever resistors we want to make whatever scaling factor we want. So you can imagine, if you wanted a 10x gain, you could choose R2 to be 10 times as large as R1. You have a 10-time amplifier.
So we call this one inverting because we have that negative sign right here. So it kind of flips your signal. And then the other kind we could have, so at the most basic level, if we think about what ways we could connect up this op-amp, we have, with just two resistors, we could do the same thing, but instead of having ground at the positive terminal and V in attached to the negative terminal, we could flip that. So say V in is at the positive terminal, and ground is with the resistor at the negative terminal. So these setups look very similar, but one is inverting, and we get this flipped signal, and the other one we call non-inverting. So we can do a similar analysis. So in this case, and the quick way to see if your circuit is inverting or not inverting is just look at where ground is. So in this case, we have this location is 0 volts. V in is at the plus terminal, which means V plus equals V minus under our ideal op-amp assumption equals V in. And now if we look at this component, as Jacob was saying, the current, in this case, the path is just simply from V out to 0. And if we assume V out is positive, then this, this path will have current flowing from V out to 0. So in particular, V out equals I times R1 plus R2. And then if we want to find V in, which we know, V in is equal to I times R1. So this gives us our relationship between V in and V out. And in particular, we have that V out is equal to V in times R1 plus R2 over R1.
And so once again, we have the scaling factor where we can choose R1 and R2 to get whatever gain we want.
And one more thing to note is that V in times, we can simplify this as 1 plus R2, and this is probably the more common form. You might see it as 1 plus R2 over R1. So this circuit, because this is 1 plus some value that's positive, this circuit will always create a positive gain. It will always amplify your circuit. It will always amplify your signal. In this case, R2 and R1 can have any ratio. So this could make your signal bigger or smaller.
So one thing to note is that sometimes instead of using the ideal op-amp assumptions, we might give a more realistic model for how to think about an op-amp. And an op-amp, right, inherently, it's like a perfect example of a dependent source, right, because we have V out, and what is V out? It's some linear scaling of these two inputs, right? And so you can also think of an op-amp in terms of like this dependent voltage source that equals like A times V plus minus V minus, like this would be ground or whatever, and this would be the output voltage, and the input terminals would be, you know, V plus and V minus. So this could be an example of an op-amp. And also, you know, in a real-world op-amp that isn't perfect like this, you know, it might have some resistance in here or something like that. And so we could ask you, you know, if we're using this model of an op-amp, now solve one of these circuits or something like that. And so you would then basically copy and paste this into where the op-amp is in your circuit and solve from there, and you could kind of forget this is even an op-amp anymore. You'd just be solving it like any other circuit with a dependent source in it. What you'll often see, though, is if you then at the end of your analysis make some nice assumptions, such as A is, you know, close to infinite, and, you know, this resistance would be very small or whatever it is, you're going to simplify to these nice values that you would get had you assumed that the op-amp was ideal in the first place. Does that make sense? Yeah.
Will we ever have to do non-ideal op-amp things with like A not being close to?
So it's possible. Like we could give you a model like this, and you might need to solve for the answer in terms of A. Generally, we would do that in order to, you know, sort of see how good our approximations are. And so, you know, sometimes what you'll get would be something like you would get this, but it would be like, you know, plus 1 over A or something like that, right? So 1 over A, if A were infinite, that would just be 0, and we'd get exactly what we wanted. If A were like 1,000,000, we would be off by 1 over 1,000,000 or something like that. But yes, we could give you some model like this, and you'd have to solve it using A, and you couldn't use the, you know, just the model we've given.
But as long as you use the condition that there's no current going into the positive and negative terminal, and you use this model, like you forget it's an op-amp, as Jacob was saying, and it just turns into a like not necessarily simple, but a dependent source problem. Okay, and we'll solve one of those right now.
Will you do that if you use a password?
Any questions about anything while we're drawing things on the board? Feel free to just shout it out. So we still have a bit of time and only one more topic left, so we're gonna give you guys like 3 minutes to start thinking about this problem, write out what your approach is. So is it gonna be superposition or nodal analysis or matrix method? And we'll reconvene in a couple minutes, talk to your neighbor.
What's
Yeah.
What's the U?
So the U is the the measured voltage. So it's not a voltage source. Is if you were going to take a probe and do a measurement between these 2 points, that voltage is U. So this is a dependent current source that is based on the voltage between these 2 points. This. What are we trying to
You're trying to find V out in terms of like the parameters given, so in terms of Vs and B and R1. One thing to note is like U is not allowed in your answer for V out, right? U is just some measured amount here. It's not some like known value or something like that.
Because like when you turn on the circuit, there will be some voltage that appears between these 2 points, and that voltage is going to then feed into the voltage here. So U will not appear in your final answer. And when you find V out in terms of I out, what that's essentially doing is finding the Thevenin equivalent of this circuit.
Is that second resistor equal to R1?
This is R1, oh, R2, sorry. so you can think about working identically in both directions.
Because on one of the homeworks, they were drawn like there's like a long line and a short lane, and then it was in series with something that was short and long. So I didn't know if like the direction of current or something was reversed, but it ended up being the answer was correct if you assume that they were both the same.
Yeah, so there are some capacitors that actually do only work in one direction. Part of that might have been wanting to define a direction that you were defining plus and minus, but if you can define plus and minus to be whatever direction you want. Okay, so we're gonna go through this. Are there any points of confusion before we go through this solution? Okay, so when we're looking at this, we see V out and I out, and this kind of makes us think of a Thevenin circuit. So we'll start by, we could do either method. In this case, I'll apply a test current. So if we add, so we'll add our test current, I out, and we'll measure V test. And let's solve this problem with superposition, for example. Yeah. So let's say the first source we turn off is, or the first source we leave on is this voltage source over here, and so we'll turn off I test. What happens when we turn off I test? We get an open. So let's see.
Well, right, so to note, right, what we're trying to solve for is this node up here. We defined ground at the bottom. And so this node up here, what we see is these are kind of two separate little loops right here, right? Like there's no connection here, and so this loop is just going to have this current flowing through this resistor, and this guy is just a voltage source and a resistor. And so we can solve for V-test in terms of these guys. We know that this current is just going to go straight down through R2. And so from that, we have that V-test equals B times U times R2. We're not done because we can't use what U is. And so we have to come up with another equation. We can look over here and note that the voltage up here is Vs, right? And so now what we really need to do is, in order to find U, we have to figure out, well, what's at the negative terminal, right? U is going to be Vs minus whatever's over here. Well, from that, right, V-test is all the way up here. This is all one node. And so if this is V-test and that's Vs, we also have that U equals Vs minus V-test. And now we have two equations for our two unknowns, V-test and U. If we substitute this formula for U back into here, we'll get that V-test equals B Vs minus Vt times R2. And then if we rearrange, we'll get that Vt equals Vs times B R2 over 1 plus B R2. Does that make sense? I might have made a mistake. Did I make a mistake? I see some confused looks. Yeah?
Can you explain again how you got the voltage at the negative side of U?
Yeah, so like we're solving for V-test, which is the voltage drop from here to here, and this is ground. So this node right here is V-test, and this is all one node, right? There's no components over here, it's just a wire. And so this negative side of U is still equal to V-test, and this side to Vs. Yeah?
So could you explain how you got V plus is VU times R2 again?
Yes, so that was because we have this loop here, and right, there's no other
path for current to escape. All of this current, BU, that goes up here, it can't go left, it has to go right. And it also can't go through here since this is open. It's all going to drop across R2. And so this voltage drop is BU times R2, and this voltage drop is precisely V test. Is everybody, yeah?
And so like because you use superposition and like turned off the eye test, you don't have to like turn it back on and turn off like.
Exactly. But one thing to note is in the process of doing this, we've just solved for this open circuit voltage. This is precisely the Thevenin voltage, right? This is the response we get from everything except the eye test that we're applying, right? So like Hannah's example earlier, we had all of those terms in terms of the independent voltage and current sources in the circuit. That's exactly what we just solved for. Now we're going to do the opposite. We're going to turn off the independent sources inside the circuit. So this voltage source is just going to become a wire. We're going to turn back on eye test, and notice that this is generally how we solve for the Thevenin resistance, right? We just turn off all of the independent sources inside, right? And we apply eye test and measure what V test is. And this analysis is also a bit simpler just because, right, this resistor R1, like notice this ground goes all the way around and up here. This is no longer VS, it's just 0 volts now because still the same ground node. So, you know, you might wonder sort of like, what does R1 do now? Well, one way to think about it is if 0 volts up here and 0 volts up here, there's no voltage drop across the resistor R1. And if there's no voltage drop, there's also no current. So we can kind of just forget it exists. It's irrelevant to the circuit. So the only thing we have to analyze is this side. In terms of this side, right, now, if we do KCL like at this node, we have these two current sources going up. They're both going to converge here, and then it all has to drop across resistor R2, right? And so that voltage drop, which is precisely V test, we're going to have the VT equals R2 times VU plus I test once again, we have to solve for what U is, and we can do the same trick as last time, right? This guy's still VT, but now this is 0. So now we see that U is actually just negative VT. And so I'm just going to go in here. So we get a minus VT, and the rest stays the same. And then if we rearrange, we're going to get that VT equals R2 over R2 minus B. But this was multiplied, right? So when we move that across, we're going to have like 1 plus B R2 times I test. And so if we wanted to figure out what the Thevenin resistance is, it's just V test over I test. So the Thevenin resistance of this circuit is R2 over 1 plus BR2. And so if we were to draw the Thevenin equivalent of this circuit, we solved for VTH earlier. It was that guy. It was VS times BR2 over 1 plus BR2. And we just solved for our Thevenin resistance. It's R2 over 1 plus B R2. And that's now equivalent to that circuit as viewed at this output port. Does that sound good?
Question. So, sorry, how did you get the voltage at U minus again?
Yeah, sorry, I'm kind of rushing to it.
This time.
Yeah, so it's the same trick as last time where we look at what voltage is here, what voltage is here.
Yeah.
Just as last time, V test is still just the same node all the way over here. But now on this left-hand side, because we killed this independent voltage source and just made it a short circuit, a wire, the ground node extends all the way around and we have 0 up there.
Okay, so before it was VS minus V test, and now it's just negative V test.
Exactly, because VS turned to 0.
Sorry, I'm a little confused why the Thevenin resistance isn't just R2.
Yeah, it's a good question. The reason is that we get this sort of weird response from the dependent source here.
Okay, so if that dependent source had been like an independent source, that would the Thevenin resistance have been R2?
Yes, because then when we turned this off, we would have just been left with a resistor.
Okay.
Yes.
So the first one found VTH and then found RTH and the second one?
Exactly. Right, VTH is your open circuit voltage. You leave the port open, you leave everything else the same, and you just measure what voltage you get. RTH, you apply an I test and you measure V test, and you turn off all of the independent sources inside. We could have also done this the opposite way. We could have applied a V test and measured I test, and then we would have found the Norton current and the Norton resistance, and the Norton resistance the same as the Thevenin resistance. One other really important thing, and I don't know if we forgot to mention this, is that V Thevenin equals R Thevenin times I Norton. It's very important to know. So if you know two, you can figure out the third. Does that sound good to everyone? If so, we'll do capacitors very quickly, but obviously feel free to leave if you have to go. Okay, so capacitors we just began to cover. They're a very cool device. They have their current, and it's proportional to the derivative, the time derivative of voltage across them. So this is how we draw a capacitor. As usual, we define the plus and the minus terminal, and the current goes into the plus terminal. One thing to note is that they work differently in terms of series versus parallel connections from how resistors work. So now, if they're in series, the equivalent capacitance is the whole, 1 over C equivalent equals 1 over C1 plus 1 over C2. But if we have two capacitors in parallel, that becomes a single capacitor where we've just added the capacitances. So it's important to keep in mind they work opposite of resistors in terms of how you combine series and parallel combinations. So oftentimes you'll have an RC circuit where you'll be either charging or discharging a capacitor. Right? So the idea here is we have this voltage source, resistor, capacitor. And so oftentimes, right, we'll call it bottom ground, we can determine the differential equation that governs this circuit. And so what we're really interested in, right, is like the voltage across this capacitor, VC. You can think of it as V out of this circuit. And so if we were to do a nodal analysis on this, it's a small circuit, it's one loop. We have one current going all the way through. Let's call it I, and let's define it going that direction. So we see, because I is dropping across this resistor, we see that V, discharge, we'll get to that in a second. We see that V minus VC is this voltage drop across the resistor, right? So that's going to equal I times R, also the voltage drop across the resistor. And then we also have our normal equation for our capacitor, and that's that I equals C dVc dt. So, I, we don't want to rely on that in our equation. That's an unknown. It could be time varying. And so we want to substitute. If we do that substitution, we get V minus Vc over R equals C dVc dt. And now we have a differential equation in one unknown, Vc. We can simplify this form, and then we'll get V equals RC dVc dt plus Vc. And now you can solve this as a differential equation. One other important way that you can sort of think about how these RC circuits work is that we have this new sort of notion of this time varying voltage or current going on. Right? When everything was just simple and linear, everything was just exacting. We have this amount of current and this amount of voltage. Nothing was changing with time. It was just immediate, whatever it is. This now has this sort of weird time varying process going on. And so what you might wonder is if I let it go for long enough, what happens to it? Like, does it just keep changing eternally? The answer is, like, in a circuit like this, where we've just sort of left it as is and let it sort of run its course, it will reach what's called its steady state. And the idea of the steady state is that no parameter is changing anymore. In steady state, the current has to be constant, all of the different voltages have to be constant, etc. And so the idea is, right, because a capacitor, the current is proportional to the change in the voltage. At steady state, there can't be any change in voltage, and therefore current is 0. So if you give it enough time, you know, current will flow in over time, but at like t equals infinity, after you've let it sit for, you know, a very long amount of time, there will be no current flowing anymore, which means that like all of the voltages will just be finalized and fixed. And so it's often helpful to sort of look at a circuit and say, what is the initial state of things, what is the final state of things, and that can help you write your differential equation just by looking at it. So we have this nice form for our differential equation, which is that Vc at time t equals Vc at time infinity, so that's the steady state, plus Vc at time 0 minus Vc at time infinity, I really did not write this well, times e to the minus t over rc. So you would get this same formula if you were to solve out that differential equation, right? When you have a differential equation, in order to solve a particular solution, you need your initial condition, right? And that's what that Vc of 0 means. In this particular circuit, if we want to figure out what Vc of infinity is, as I was saying before, the current goes to 0 as t goes to infinity. If the current's 0, that means that there's no voltage dropping across the resistor, which means that all of this voltage V drops across the capacitor C. And so in this case, Vc of infinity equals V. And Vc of 0 would be some initial condition that we would have to specify for you. I realize that was very fast. Did that all kind of make sense? Do people have questions about any of that? Oh, yeah.
So when would that equation not hold and we have to do the compute ourselves?
So in a much more complex circuit, it might not. I think it still would. The one thing to note though is that, right, like this idea of like the V of infinity and V of 0 and V of infinity, that's sort of a generic idea. But this e to the minus t over rc, the fact that we have rc in here, that's very dependent on the specific circuit. Right, so like one very simple modification is like, what if I had two resistors here, R1 and R2? Like which one would show up there? It would be R1 plus R2 because they'd be in series with each other, and so it would simplify to this case again. But that time constant could change in a more complicated problem, and that actually brings us to the final point we were going to talk about, which is that sometimes if you want to analyze a circuit with a capacitor, if it's some really complicated network surrounding a capacitor, it might be hard to see sort of what the time constant should be. And so one thing that you can do is you can isolate the capacitor, sort of rip it out, and view the entire rest of the circuit with all of its linear pieces as a black box and solve for the Thevenin equivalent of all of that. Because this, as far as we're concerned, this voltage source in series with a resistor, that's a Thevenin equivalent. This could be any circuit, any linear circuit we want, and then we attached it to a capacitor. And so we could give you some like super complex circuit. We could give you the circuit that Hannah was solving over there with the dependent source, and then just put a capacitor at the output and tell you to find the time varying voltage of the capacitor. The way you do that is you view everything outside the capacitor as a black box, solve for its Thevenin equivalent, and then you draw this exact circuit, and then you can use that equation to solve that circuit.
So this equation would still hold. Instead of V, it would be phi Thevenin, would be what you were looking at. And the time constant will always hold. So you did something similar to that on the lab 5, where you wanted to, formally you wanted to separate, there were those two capacitors, you wanted to turn that into some equivalent capacitor network, and then you simplified the left-hand side of that circuit, and you turned it into some Thevenin equivalent circuit. And so when you're thinking about what the initial voltages and the final voltages, you would be reducing that to what is the initial Thevenin voltage, what is the final Thevenin voltage, and that sort of thing. Okay, so we'll stay around for questions. We realize we are out of time, so come and talk to us.
Good luck, everyone.